lecture 22 on essentials of topology. In this lecture, we will study the concepts of product and box topologies. Specifically, we will study the concept of topology on arbitrary product of sets. Let us recall the concepts which we have studied in the previous lecture. Begin with the concept of product topology. We have seen that there were two ways to characterize the product topology. One was by using the concept of basis, and the second was by using the concept of subbasis. Begin with the characterization of product topology by using the concept of basis. What we have seen that if we are having two topological spaces x1 tau 1 and x2 tau 2, then the collection, which is Cartesian product of G1 and G2, G1 belongs to tau 1 and G2 belongs to tau 2. This is basis for a topology, and we call that topology product topology on Cartesian product of x1 and x2. We have also seen that we can reduce the structure of this basis, and that characterization was given in this particular fashion. That is, if we are having two topological spaces x1 tau 1 and x2 tau 2 with their basis as b1 and b2 respectively, then the collection of Cartesian product of this form of sets, that is b1 cross b2, where b1 belongs to the basis of topology tau 1 and b2 belongs to the basis for topology tau 2. This collection is basis for product topology on x1 cross x2. Moving to the next, let us see the subbasis for product topology on x1 cross x2. What we have seen that if we are having two topological spaces x1 tau 1 and x2 tau 2, and the collection, that is a set pi 1 inverse G1, G1 belongs to tau 1, union pi 2 inverse G2, G2 belongs to tau 2, where pi 1 is a projection map. This was defined from x1 cross x2 to x1, and pi 2 was again a projection map that was defined from x1 cross x2 to x2. If we are considering this b dash in this particular form, we have seen that this b dash is a subbasis for the product topology on x1 cross x2. So in the previous lecture, what we have seen, actually we have tried to construct product topology on Cartesian product of x1 and x2 when the topology tau 1 was given on x1 and tau 2 was given on x2. Note that this Cartesian product can be generalized for n topological spaces, meaning is to say that if we are having topological spaces x1 tau 1, x2 tau 2 and x and tau n, then this collection, that is Cartesian product of G1, G2 and Gn, where Gi belongs to tau I is from 1 to n, is a basis for product topology on Cartesian product of these n sets, that is x1, x2 and xn, and their Cartesian product is denoted by using this notation. Moving ahead, similar to the concept of product topology on two sets, and if basis was given for only two topologies, the same concept can be generalized for n topological spaces, meaning is to say that if we are having b1, b2 and bn as a basis for x1 tau 1, x2 tau 2 and xn tau n, then this collection, which is Cartesian product of b1, b2, bn, where b1 belongs to basis for topology tau 1, b2 comes from basis for topology tau 2 and bn comes from basis for topology tau n. This is a basis for product topology on Cartesian product of these n sets, that is x1, x2 up to xn. Again, we can give the sub-basis characterization for product topology on this product of n sets, that is, if we are having n topological spaces, then this collection B dash, which is union of pi I inverse Gi belongs to tau I. This is a sub-basis for product topology on the Cartesian product of x1, x2 up to xn. Here this pi I is again a projection map, and this projection map is defined like this pi I, which is a map from x1 cross x2 cross xi to xn to this xi, sending this x1, x2, xi up to xn to xi. Moving ahead, what we have seen that we have already seen the Euclidean topology on R2 by using the concept of basis as well as by using the concept of metric. So the Euclidean topology on R2, it can be seen that this is the same as the product topology on the set R cross R, that is R2, because what we have seen that collection of open rectangles for a basis for Euclidean topology on R2, and when we are using the concept of product topology on R2, again the collection of open rectangles for a basis for product topology on R2. This concept can generalized for n number of sets for n greater than or equal to 2, and what we can conclude that Euclidean topology on R is same as the product topology on the Cartesian product of these n sets, that is given by R. Moving ahead, let us try to visualize the product of sets in a different way. Meaning is to say that what exactly we have seen, that if we are having n sets, then the Cartesian product of x1, x2 and xn, this was given as collection of n tuples x1, x2 and up to xn, where x1 belongs to x1, x2 is from x2 up to xn from xn. Note that what we are writing here, this is in x1 and this is, we say that this is corresponding to 1, this is in x2, this is corresponding to 2, and in the same way this is corresponding to en. Now this element of this Cartesian product can be visualized as a map f from a set that is 1, 2 up to n to union of these xi's i's from 1 to n, such that this f of I belongs to xi, and by notation this f of I is denoted as xi. So what we can say that the Cartesian product of these n sets, this can be given as collection of maps f from this set 1, 2 up to n to union of I varies from 1 to n xi, such that f of I belongs to xi for all I, and that I varies from 1 to n. And by notation, this Cartesian product can be denoted by product of xi, I varies from 1 to n. Now what will happen if we are replacing this set by an arbitrary set, that is an arbitrary index set. This is our motive. And if we are replacing this set by an arbitrary set I, we can define product of an indexed family of set. Let us take this is an index family of sets, then the product of this xi, that is given as collection of all maps f from I to union of these xi, where fi belongs to xi for all I in I. One point to be noted here, that whenever we are taking this indexed family of sets, we are assuming that this xi is a non-empty set for all I in I, and if xi are non-empty, their product will always be a non-empty set, and this is possible because of axiom of choice. Having the idea of arbitrary product of sets in mind, let us see the concept of topology on this arbitrary product. What we will see? We will discuss two concepts here. One concept will be the concept of a topology on this product of sets by using subbases, and another we will see by using the concept of basis. Begin with the concept of subbases. Let us take a family of topological spaces, and this is indexed by a set I. Then for each I belongs to I, if we are defining the projection map given by pi I, that is from product of sets xi to xi, which is a map defined as pi I f is equal to fi, where f belongs to product of sets. One thing will be interesting here, that if we are taking a gi which is subset of xi, and we are taking this gi from the topology on xi, question is, what about the inverse of this gi under this projection map pi I? By the definition, this will be collection of all maps in this product of sets, that is f belongs to this I belongs to I xi, such that pi I f belongs to gi, or it can be written as collection of all f from this product, such that by using the definition of this projection map, this fi belongs to gi, or it can be written as the product of something like I belongs to I, where this ai is equals to gi and aj equals to xj for I not equal to j. Interestingly, if we are taking this gi as xi itself, what about the value of this pi I inverse xi? Obviously, this is nothing but the product of xi I belongs to I. Now let us take collection of such sets. Interestingly, they will provide the concept of subbasis for a topology on this product of sets. What exactly I want to say, that if we are taking union of I belongs to I and pi I inverse gi, where gi belongs to tau I, and this is obvious that tau I is a topology on xi, then this for a subbasis for a topology. One thing is clear from here, that if we are taking this x as this product of xi I belongs to I, what we have already seen, that the pi I inverse xi is equal to X itself, and therefore this collection will always be a subbasis for a topology. Now if this is a subbasis, what we know that beginning with a subbasis, that is B dash, we can move to a basis, and from basis one can move to a topology. Let us denote this product topology by tau p. If we want to visualize that how an element of B can be look like, then if we are taking any B belongs to this B, so this B can be written as pi I1 inverse of GI1 intersection pi I2 inverse GI2 intersection pi IN inverse GIN, that is finite intersection of members of B dash. Then, and this will be equal to product of some sets AI, I belongs to pi. And how this AI will look like? Actually, this AI will be something like GI if I belongs to this set I1, I2 up to IN, and this AI will be equal to XI otherwise. So what we have seen that in case of basis for product topology, which is obtained by using this B dash as a subbasis, an element of this basis can be expressed in the form of the product of sets, where these sets will look like in this form. Moving ahead, let us see in the topology on this Cartesian product by using the concept of basis. If we have a indexed family of topological spaces, then this collection, that is the collection given as the product of GI I belongs to I, where GI belongs to tau I, this is a basis for some topology on product of the sets. We call this as a box topology. It is going to be interesting here. We have already seen that if we are taking two topological spaces, even if we are taking n topological spaces, then such collections provide the same topology on Cartesian product of sets, but we are using a different name as both the topologies are going to be different. We will discuss in detail after completing or after seeing this concept. So question is whether this B is a basis for some topology on product of the set. Answer is yes, because if we are taking X as the product of these sets, Xi I belongs to I, then note that this X can be expressed as union of members of this B, because this set itself is a member of this B. Also, if we are taking two members from this B, let us take B1 and B2 belongs to this B. Then how this B1 and B2 will look like? Let us take this B1 is something like product of GI, I belongs to I, and this B2 is product of HI, I belongs to I. If we are taking any F in this B1 intersection B2, that is precisely the intersection of this product of I belongs to I GI intersection the product of HI, I belongs to I, and this is nothing but this is product of this GI intersection HI, I belongs to I. And note that if we are taking this as B3, this B3 will also belongs to B. Why? As this Gi and Hi belongs to tau I, this Gi intersection Hi also belongs to this tau I. Thus, there exists B3 in this B with the feature that F belongs to B3 is subset of B1 intersection B2, and therefore this collection is basis for some topology on product of these sets. Let us summarize what we have seen, that if we are having an indexed family of topological spaces, then the box topology, let us denote this by tau b, on the product of these sets xi has as basis element all the sets of this form, that is the product of gi, gi belongs to tau I belongs to y. If we are coming to another topology, what we have seen, that topology was the product topology on this set, and let us denote this topology by tau p, and note that this topology has as basis all sets of the form product of gi, I belongs to I, where gi belongs to tau I belongs to I, with the condition that gi equals xi except for finitely many values of I. From these two, it is clear that in case I is finite, what will happen? This topology, that is box topology and product topology, will be same because their basis will be same. But what about if this index set I is not finite? For example, why not let us take this set I as set of natural numbers? What one can see that this product topology is strictly coarser than this box topology. Question is, how is it possible? Let us see it. What we have seen are, if we are taking a member G of this product topology, then how this G can be expressed? G can be expressed as union of members of basis, and what we have seen that for product topology the members of basis will look like in this form, that is product of gi, gi belongs to tau I, with the restriction that gi equals xi except for finitely many values of I. But note that such products are also the member of basis for box topology, and therefore this G will always be in box topology. That is, this product topology will be coarser than box topology. But if we are taking an element of this box topology in this particular form, that is given by G, which is given as the product of gi, I belongs to I. Note that every gi is a proper subset of xi. Then what will happen? From the construction, it is clear that this G is a member of basis for box topology, and as the basis is always a subfamily of topology, so this G will be a member of box topology. But question is whether this G is a member of product topology. Answer is no, because for the product topology the basis elements look like as product of gi, I belongs to I, with the condition that gi equals xi except for finitely many values of I. But G we have taken here, this is the product of gi where none of gi equals to xi. So what we have seen, we have discussed two topologies on arbitrary product of sets. One was generated by a basis and one was generated by subbasis. In case when I is a finite set, both topologies coincides, that is, both are equal. Even we have seen that product topology is strictly coarser than box topology. These are the references. That's all from this lecture. Thank you.